So, yes. A little bit of an agenda beforehand. Just introduce the problem, that what we were trying to do, basically, how we were trying to evaluate the performance of Anycast. Then we'll look at how the ways we try to measure latency performance, how to evaluate the benefit of an individual node in an Anycast cloud, a couple of slides on stability, and then, if we have time, a couple of routing issues that we encountered during in the K deployment that are non-obvious, and I'll discuss those if I have time. So to figure out if Anycast is effective or not, we need to look at the goals. So the goals are to provide resiliency. That's the main goal, to avoid denial of service attacks, to spread load over multiple servers, and to increase performance. But the feeling that I have, and that other people have, is that we don't really understand how Anycast affects performance. At least 6 of the root servers are Anycasted, and we have hundreds, I think 112 or something, nodes spread around the world, but we don't really know how this affects performance. So this is an initial, these are initial methodologies that we can use to try to quantify that. So, how do we measure latency? So the idea is, in an ideal world, if the Anycast deployment were perfect, then we would throw the routes into BGP. BGP would work its magic, and every client of the root server would see the instance of the root server. I'll use node from here on. We'll see the node with the lowest round-trip time. Does it do this? Well, we can, if we had access to all the clients of the root server, we could just use, measure the RTTs to the K IP address, or to the IP address of whatever root server we're measuring. I'll use K because we did this work on K, but we are very interested in taking this to other root servers as well to see how deployment affects performance. So for every client, we can measure the round-trip time of a query to K, and then we can measure round-trip times to the queries of all the other nodes that are deployed. And in our case, we did it for the global nodes, because the local nodes won't be reachable from most clients. And then we compare the results. So the round-trip time to the K IP address gives us an idea of what the query time of what the time of a query to K will be, and the time to the addresses of the other global nodes gives us an idea of what performance we would see if BGP had chosen that node. So when we compare these results, if we simply divide one number by the other, if we get a result of 1, that means that BGP is picking the right node. It's choosing the node with the best performance. If the value alpha is greater than 1, then BGP is making the wrong choice. It's giving us, a client is seeing a node with worse performance than it would be able to see. If alpha is less than 1, then we're probably seeing a local node. In fact, in every case, we were seeing local nodes. So we did these measurements from both sides. First of all, we used the TTM network, which is about a network of about 100 boxes spread around the world, mostly concentrated in Europe. And we simply used dig to run the queries. We did a hostname.bind query to find out which instance, which node of the server was answering the query. We extracted the RTTs, took the minimum of 5 queries, and we calculated alpha. Just to make sure this was a fair comparison, we checked the paths to the single node interfaces before we did this, and the paths that we see to the single nodes are the same in almost every case. I mean, the path to the K root IP address in almost every case is the same as one of the paths to the global nodes. So this is a fair comparison. So these are the probes we have. As you can see, they're mostly concentrated in Europe. We'll see how that affects our results later when we compare it to our server-side measurements. So these are the results. I believe these were on in April 2006, and so what do we see here? On the y-axis we have the value of alpha. Remember, 1 means BGP is choosing the right node. Greater than 1 means BGP is making a mistake, and that's the factor of the RTT we get. So, for example, 2 means that our RTT is double what we would have if BGP picked the right node. And lower than 1, and also marked with these, I don't know if you can see them, these circles are the values for local nodes, test boxes that see local nodes. So if we exclude the local nodes, which are for the most part less than 1, except for a few cases, and we see that most of the values are actually pretty close to 1, which means that for most of our test boxes, the BGP is doing a pretty good job. So these are graphs which exclude the effect of local nodes, which make it easier to compare these results. The deployment on the left is the way we had it in April 2005, i.e. we had London and Amsterdam, and then a few, about 10 or I think 11 local nodes. And in 2006, we had 5 nodes. And as you can see, they mostly look the same. Most of the results are clustered around 1, which means that BGP is doing a pretty good job. Most of the cases, we get the best performance. Just to make sure this wasn't a chance event that happened while we were running our measurements, just to make sure we didn't get lucky, we took the average of that. And so this is the outlier you see here is TT103. I'll get to that later. I'll explain later why that value is so high. But when we calculated the average over time, we excluded this box. So we plotted the average value of alpha, averaged over all the test boxes over time, every hour. And the results are pretty consistent. The average is a little bit higher than 1, and it's mostly consistent over time. So this is not a chance effect. This seems to be quite stable. So that gives us a reasonable picture. Everything seems to be fine from where we see it. However, the measurements we do on the client side are biased because the test boxes are mainly in Europe. Because we only have a limited number of them, they're order of 100. So definitely not the same order of magnitude as the client population. And they obviously don't necessarily reflect the distribution of clients of K. So what do we do? Well, we can do it the other way around. We can ping the clients from the server nodes. Doing this, we can play with a much bigger data set, which is about 1 million client IP addresses that we used, and this obviously measures the effect on the actual clients. Okay. So what do? We keep packet dumps of queries that go into K. So we process these packet traces. We take out a list of IP addresses. And we, from all the global nodes of the K Anycast cloud, we ping all these addresses. And then for every address, we calculate alpha, as stated before. So the RTT to the K node divided by the RTT to the node in question. We took 6 hours of data for that, 6 hours of dumps, which gives us just under 1 million IP addresses, 246 million queries. And this is what comes out. So basically, 50% of the 50% of client IP addresses are actually hitting the node with the best performance. The rest are seeing varying performance penalties, with about 10% having hefty performance losses, well, 4 times slower. But most of our clients are doing pretty well. The results are not as good as those seen by TTM. TTM sees very good performance, and that is probably because most of the TTM boxes are concentrated in Europe, which is very well provisioned by K, which has 2 nodes in Europe, 2 global nodes. So, yeah. seen from TTM, things are very good, and it doesn't seem to depend on the deployment we had. When we moved from 2 nodes last year to 5 nodes this year, it doesn't seem to make a difference. BGP still seems to be able to discriminate. If we look at the total K client population, things are not so rosy. So another question we looked at was how many nodes are enough? Does it make sense for us to deploy more nodes, or have we reached the point of diminishing returns? To answer that question, what we can do is, well, the first step we can do is evaluate the benefit of existing instances. And this will hopefully tell us at which point of the curve we're on, and tell us if it makes sense to deploy more nodes or not. So how do we measure what the benefit of a node is? Well, we can simply quantify how much performance would be worse if that instance didn't exist. So if we assume optimal instance selection, which means that every client sees the instance with the best performance, then it's easy, because all we need to do is take the numbers we have and do divisions. So the fact that we assume optimal instance selection gives us an upper bound to the benefit of a node. But this is okay, because we're trying to figure out whether we've reached the point of diminishing returns or not. So for every client, we see how much its performance would be worse if a given instance didn't exist. And we have the numbers for that because we ping all the clients from all the server nodes. So for every client, we assign a number beta, which is the loss in performance that client would have if a given server node was knocked out. So for every client, we have a value of beta for every node. So a client might suffer. Suppose a client's performance would get worsen by a factor of 2 if the Amsterdam node didn't exist. Well, then in that case, the beta for that client for Amsterdam is 2. So then we plot the beta for every node, and this gives us an idea of how important that node is. So how do we read this graph? This is a graph for links. This tells us that about almost 90% of clients wouldn't see a big performance hit if links were taken away. So about 10% would get worse, and the number of clients that would get seriously worse is very, very low. Okay, this is what the geographical query distribution, the geographical client distribution looks like for the links node. We'll see. For other nodes, this node is fairly spread out. We'll see for other nodes that that's not the case, and we'll discuss how that impacts the graphs we see. This is the Amsterdam node, similar to London. If the Amsterdam node were to be turned off tomorrow, only about 20% of clients would suffer a performance penalty. So this is kind of unexpected, because these are the busiest 2 nodes, and they do see a lot of clients, and they are important to the K deployment. However, if we plot this for both AM6 and links taken together, i.e., if neither of those two nodes existed, then we would get substantial performance penalties. About 65% of the clients wouldn't be affected, but most of the others would see substantial performance hits. About 20% would get 4 times worse. About just over 10% would get 7 times worse, and so on. So taken together, the links and AM6 nodes are important. So these numbers show us in a fairly solid way that the 2 nodes in Amsterdam and London are pretty much redundant to each other, but taken together they're important. Tokyo. Tokyo is the best node for very few clients, but those clients that it does have tend to be very badly served by other nodes. So there's about the 10% of clients which would get very, very, very badly worse if Tokyo didn't exist. So it does provide a benefit. These clients are mostly, as you can see, in Japan and in Asia. obviously, which is an area which we serve only with Tokyo node. The node in Miami we have at NAP of the Americas provides moderate benefit for some clients. It handles a lot of traffic in the US and in South America. So these clients would be very badly served if they were to go to Europe or to Tokyo, for instance. The Delhi node is not particularly effective. It turns out that most of our clients would be better served by somebody else. So this is the geographic distribution of clients. Not much to see here. So once we have these numbers, we can try to condense the graph into one number so that we can have an idea of how effective a node really is. We can try to put a number on the effectiveness of one particular node. How do we do that? Well, we take the beta values for all the clients of a given node, and we take the weighted average, where the weights are the number of queries that that client sees, that the client sends, sorry. So, simple weighted average. And what comes out is, so what do we expect? If the value of the benefit value B is 1, then that node basically doesn't provide any benefit at all, since it's a weighted average of beta, and beta is equal to 1 if the node doesn't provide any benefit at all. And so if we look at it, the Europe, i.e. links and M6 taken together, are the most important factor. If those were taken away, performance would suffer very, very badly. Tokyo is also pretty important because the clients it does serve tend to be very badly served by other nodes. And the Miami node is not so effective because the performance impact of taking it away would only mean that clients get to go to Europe or Tokyo, whichever is closer, which is not a big deal. And the Delhi node is pretty much, well, not very useful. So, wrapping that up, so did it make sense to do Anycast? Well, what we can do is we knock out everything except for links. In 1997, we only had the links node until the M6 node was deployed. So the dark red or brown curve here shows that 10% of clients at the best wouldn't notice, and about 85% of clients would get worse. And the benefit value is 18.8. So it does work. Anycast does work for us, and it has brought a substantial performance improvement. So a few words on stability. Obviously, the more nodes we deploy, the more routes compete in BGP, and the more churn. And obviously, if we have TCP DNS queries, or if we have per packet load balancing and UDP fragments, then that might be a problem if if a client's best node changes while the query is being done. In that case, the query fails. So we try to evaluate the impact of this problem by measuring at the server nodes. We looked at the node switches that actually occurred. So we basically take the packet dumps from all the global nodes. At the time, there were only 2 global nodes. Yes, actually, we did them on 5 as well. We extracted all DNS traffic, and for each IP address, we remembered where it was last seen. And if it then is seen at another node, then we log a switch. The K nodes are only NTP synchronized, which should be enough to catch most synchronization problems, but they're not microsecond synchronized. So these are the results. The important numbers here basically are these ones. The fact that in 5 hours of data, we saw only 0.06% of queries used a different node. For only 0.06% of queries, the client used a different node than it had for the previous query. And only about 0.33% of the client IPs actually switched once or more. So this has increased significantly from the two node data that we have 1 year ago, but the results aren't directly comparable because they're taken on different timescales, and they're still very low. So we don't see a serious problem with instant switches. At least in our deployment, doesn't seem to be a big problem. So, a couple words on the routing issues we faced. We saw basically a couple of problems that can lead to performance problems. Different prepending values announced from different nodes, and no export causing various kinds of trouble. Both loss of reachability if it is honored, and also bad performance if it's not. So, as I said, this is the data from April 2006. The outlier is TT103. It doesn't actually have a value of 10. It has a value of 200 because the graph is, the axis is cut. So what happened there? So TT103 is in Yokohama, and the Tokyo node is only about 2 milliseconds away. But the query goes to Delhi through Tokyo, Los Angeles, and Hong Kong, and it gets served by the Delhi node, which results in a round-trip time of 460 milliseconds instead of 2, and therefore a value of 208. So what is the problem? Thanks again to Randy Bush and Matsuzaki for giving us the BGP information here. What happened is that we were announcing Tokyo with four prepended 4 times, and Delhi prepended 3 times. And so the paths that the best path was seen by TT103 was the path to the Delhi node. So this can lead to very, very bad performance for some clients, and that's something that we need to take into account in this kind of deployments where we use prepending to stop global, to give an advantage to local nodes. Another thing that can happen with no export is that it can lead local nodes to be worse than global nodes. This is an example that was since been fixed, so we couldn't debug it much. But basically, TT89 was seeing a local node, the DNIC node, with 30 milliseconds instead of going to London. Why is that? Well, because local nodes announcements, if no export is ignored, they get announced to customers. And since their announcements are shorter, when they compete with the announcements for the global nodes, they win. So if no export is not honored and ASs are large, then it can lead to big performance problems. Another thing it can do is lead to loss of reachability. Thanks to Randy for pointing this out. Basically, we use no export to prevent local node announcements from leaking to the internet and from attracting traffic from elsewhere. But if we have an AS whose providers all peer with a local node and who all honor no export, then these providers will be forbidden from announcing the route to K to that AS. So that AS will see no route to K at all. So it wouldn't be able to reach the K at all. So what we do here is we announce a less specific, and from one of the nodes, it doesn't matter which one, we announce a less specific prefix, and if the service prefix, the /24, which is the K network, is not announced due to no export, then the customer will see the /23, the less specific. And this does not affect routing in any way, because what happens is once the packet reaches one of the upstreams, it's routed according to the upstream's routing policies, i.e. according to their best route, and therefore it goes to one of the local nodes. So this is more or less how it works. If the customer in the bottom left appears with 2 ISPs who both have the route to local node with no export, and those routers have a best path to the local node, and they can't announce it because they honor no export. So the customer has no route. And therefore, if we announce the aggregate, then the packets from the customer can reach the upstream, because the customer does have a route to the K IP address, and once it's there, it will get routed to the local node that ISP is chosen. So that's it. If there are any questions, I'm happy to take them.
Mark Oster's VeriSign. I did a similar sort of study on this about 2.5 years ago, and I saw much higher sort of switching rates. I was wondering if you could define what switching really means. If you ping pong between two different sites, is that one switch?
We define a switch as an IP address that's seen as a client of one node at one point in time, and then is seen as a client of another node subsequently. That is a switch.
Okay, but if it ping pongs, is that still one switch? It goes back and forth?
No, that's two.
That's two? Okay.
That's two.
Okay. Interesting.
Again, this probably depends on deployment a lot.